All right. So we kind of switched gears last class, talking about hypothesis testing. We're going to be doing a lot of that over the up into the next exam, also even after the exam. So really try to, if you have any questions as we're going through it, make sure you kind of stop me so we make sure we get a pretty good handle on what we're doing here. So we left off last class kind of using that court case analogy, just to kind of a different way of thinking about null and alternative hypothesis, right? So what we're going to do, right, we're not doing a court case example. What we're going to be doing is trying to test for where that true population mean is, okay? So we have our null and our alternative hypothesis. Just a reminder, we write the null H subscript 0, 0 kind of being null, and then the alternative H subscript A, right? So we have three different types of tests, right? A greater than, a less than, and a not equal to. So remember, the null is what we're assuming is true. Okay? So here we've assumed that the true population mean is less than or equal to some value. So this mu subscript 0, in practice when we write this out, that will be a number. That'll be the number that we're assuming the true mean is less than or equal to, or greater than or equal to, or this third one, we're just assuming that the true population mean is exactly equal to a certain number. Okay? So we look at kind of thinking about the null alternative being, we talked about they're kind of complements of each other. Notice if I'm assuming that the true mean is less than or equal to, say, 50, the alternative hypothesis would be that it's greater than 50. Right? Oh, we got a bunch of people coming in. There we go. So if I look at the names of these tests, they line up with whatever's in the alternative hypothesis, right? So notice if there's a greater than sign, that's a greater than test. If there's a less than sign in my alternative hypothesis, that's a less than test. And if there's a not equal to sign, it's a not equal to test. Right? So we call these two, right? Sometimes instead of greater and less than, I'll call these right and left tailed, right? So greater than, right? If I'm thinking about a distribution, if it's greater than, it's on the right side of the distribution. So greater than or right tail test. Less than, I'm looking at the left side of that, right? Less than to the left, so left tail test. And then not equal to, you can imagine if I'm assuming that the true population mean is equal to 50, well then if I see something on either side, right? Let's say I see 62 or I see 41. Those are both evidence that the true mean isn't maybe 50, right? It doesn't matter if it's above or below there, because on either side, that would be evidence that goes against what I've assumed to be true, right? If I assume that, that the true mean is less than or equal to 50 and I see 41, well, that's okay. That actually supports the null. That would not be evidence against the null. So here, when we have this equals in our null hypothesis, we also can think about this as kind of a two-sided or a two-tailed test, okay? So here, only one side matters. And as we work through more examples, I'll kind of reiterate this. And then here we have a not equal to sign in the alternative hypothesis, kind of both sides matter, both tails matter, we have a two-tailed test, okay? And I don't know if we'll quite get there today to making sure, we understand the importance of this, but once we start to calculate things like p-values, it becomes important whether or not it's a one or a two-tailed test, right? We do things a little bit differently, okay? So, this first step to actually constructing a null and alternative hypothesis seems pretty easy, but identify what population parameter you're interested in. Are we looking at a population mean, or are we looking at a population proportion? Then determine, is it a one or a two-tailed test? Okay. Right? After we have, is it a one or a two-tailed test, we're always going to put the equality, just for the sake of this class, we're always going to put it in the null hypothesis. Right? Eventually, we'll work through some examples at some point over probably sometime next week. I'll show you why it doesn't really matter if we include the equality here. But technically, to be correct, we should be putting the equality in that null hypothesis, right? As opposed to the alternative, okay? So, if we go back to the example we had from last class, we kind of set up this question that maybe I want to test for whether or not the average mass market beer has a lower ABV than this Bell's Two Hearted, which has an ABV of 7%. So what I'm saying is, what I want to test for, that's my alternative hypothesis. I want to see whether or not the mass market beer ABV is lower than 7%, right? Or Two Hearted. So I'll assume the opposite is true. I'll assume that it's not lower. Or, in mathematics, I'll assume it's greater than or equal to that 7%. Right? So whatever I want to test for is my alternative hypothesis. I want to test whether or not the average mass market beer is lower than 7%. That's my alternative hypothesis. I assume the opposite is true to get my null, which is that it's greater than or equal to that value. Okay? Any questions on that? It shouldn't be too terribly tough. I think just seeing more examples kind of helps identifying what the null and alternative are. So if I look here, what type of tailed test do I have? Well, I have a left-tailed test, right? Because I have a less than sign, or a less than or a left-tailed test, because there's a less than sign in the alternative hypothesis. So really where this comes from is the idea that if I assume, all right, let's for a second assume that the population mean is 7%. That would mean that the sample mean distribution would have to be centered around that. It's a terrible 7. Right? Centered around that. Well, if I'm assuming it's greater than or equal to 7, if I see a sample mean anywhere in this range, that actually supports the null. Right? So if I have the null is that the mean is greater than or equal to 7, all these values would support the null. The only sample evidence I could find that goes against what I assume to be true is if I see something down here, right? So that's why when the alternative hypothesis is a less than sign, what that's really saying is only sample evidence that we see below that assumed true range for the population mean, only evidence on the left side is going to be something that we could reject the null at, right? Or evidence that goes against the null, right? So less than sign, when you think about this as a less than or a left-tailed test. This is kind of just a different way of seeing that. Okay. So what if instead, the question I was interested in is, an economist wants to establish that the mean retirement age is different than 67. So if I'm saying different than 67, that's what I want to test for. That's what I want to find. What am I really saying there? I'm really saying is the mean retirement age anything other than 67, not equal to, right? So that's what I want to find. So that's my alternative hypothesis, right? I'll assume the opposite is true to kind of stack the deck against myself. So if I want to test for whether or not it's different than 67, I'll assume it's actually equal to 67. So my null hypothesis would be that the true population mean is equal to 67. My alternative, that's what I wanted to find, or that's what I was originally wanting to test for, which is that it's not equal to or different than 67. So anytime you see this terminology of being different than, or does it differ from, you should be thinking two-tailed tests, or these not equal to tests. But what you're really saying is any other value than 67 is what I think, right? So I'll assume the opposite is true, which is that it's exactly equal to 67. Okay? All right. Anything else I want to say at this point? Yeah, I'll set us up for this type 1 error discussion. So let's use this idea of is it equal to 67? Right? So if I assume that the mean retirement age is equal to 67, I know that my sample means should be normally distributed around the population mean, which I'm assuming is 67. So if I see a sample mean up here, and let's say, I don't know, say it's 72, right? I know that depending on the variance of the distribution, but for the sake, we can kind of just think about the distance away. If the true mean was in fact what I assumed to be true, which is 67, it would not be very likely that I see a sample mean of 72, right? And so this is evidence that's inconsistent with the null hypothesis, but is it inconsistent enough, right? Because I could think about, if I saw a value of like, what, 67.2, well, that's also evidence technically that goes against what I assume to be true. But we know that seeing a sample mean of 67.2, if this was in fact the true population mean, this would be way more likely for me to see than this would, right? Because it's further away from that mean, or we could think about it has a lower probability of seeing something that far away or even further from that assumed true mean. Okay? Now, let's assume for a second that we can like observe things after the fact, right? So I'm assuming that the mean is 67. I see a sample mean of 72. You know, we'll go through the exact steps of how I can get to this decision today. But let's say I'm like, well, look, if the true mean was 67, it seems very unlikely that I would see a sample mean of 72. So unlikely that it's probably more likely the case that this true sample mean is probably like 71. Right? Because if the true mean was 71, it'd be a lot more likely I would see the value I did for my sample mean. Okay? But let's say we go back and we say, no, in fact, after the fact, we observed it, we got the population data, and the mean retirement age is 67. Well, then we would have been rejecting this assumed true value if we saw the sample mean of 72, when we shouldn't have been rejecting it, right? Now, there's a low likelihood that we saw that sample mean, but we just so happened to, right? So when we reject the null hypothesis, or when we reject what we assume to be true, when in fact we shouldn't have, we'll call those type 1 errors. Right? And don't worry too much about kind of the distribution. I'll go over that again more specifically about how we can actually identify these type 1 errors on the distribution. But the idea is that we saw sample evidence that looked like it was inconsistent with what we assumed to be true, and so we rejected. But when it kind of comes back out, if we were able to observe the population data, we figure out we shouldn't have been rejecting. We rejected even though we shouldn't have been. So that's a type 1 error. Type 2 error, we won't go over it a little bit today, but we're going to save the discussion probably even till next Monday to go more in depth into this. But it's when we fail to reject the null when we in fact should have, right? So type 2 error is just kind of the opposite of the type 1 error. Right? Another way of thinking about this is if I reject the null when in fact the null is false, I'm making the right choice there. If I fail to reject the null when it's true, well, yeah, I was making the right choice there too, right? I didn't reject it and it ended up being true. If I reject the null when in fact it was true, I'm making a type 1 error. If I fail to reject the null when in fact it wasn't true or it was false, that's a type 2 error, right? So maybe this different combination, it's like, here's what the true state of nature ends up being. Here was my rejection decision. You can think about these were the two scenarios where I'd be correct, my type 1 error and type 2 error here. I think the one we're really going to focus on is type 1 error, which is when I reject the null when in fact I shouldn't have been. It was actually true. Okay. So this type 1 error, we're actually going to be able to identify with specific values, which we'll call alpha. Okay. So alpha is going to be the probability that we make a type 1 error based off of the one sample mean that we see. Okay. Now, another way of we'll start to talk about this is significance levels. So if alpha is, say, 0.01, because alpha represents a probability, 0.01 would be a significance level of 1%. Right? So we also can take it a step further, which I probably won't really need today, but kind of moving forward we might use as well. So I just figure I'll get it out of the way now. Well, I should probably technically, here's my heading. So 0.1, 0.05, and 0.01. I'm going to look at those three alpha values. Those are my three different kind of type 1 errors that I would maybe want to make. Those would correspond to significance levels of 10%, 5%, and 1%. So if I'm making errors, 10% of the time I'm going to make a type 1 error. What percent of the time am I not making a type 1 error? Yeah, right? So we can actually think about these almost like we did with confidence intervals, where if I know the significance level, the confidence level is just whatever would get me to 100, right? If I'm making errors 10% of the time, I'm not making errors 90% of the time, right? So the 10, 5, and 1% significance levels we can think is corresponding to the 90, 95, and 99% confidence levels, okay? Any questions on that before we get going? Does the sound still okay? See if anyone. Well, hopefully it is, I guess. Hopefully that you're not just not hearing me. That's why you're not responding. Okay, thanks. So let's go back here. So this level of alpha or this type 1 error is going to be something that generally like you're given in the problem or like you're selecting as kind of the researcher, right? It's kind of like with confidence intervals. We could build a confidence interval at the 90% level. We could build another confidence interval at 95. Here, we're going to be doing a hypothesis test at the 1% significance level. We'll do a hypothesis test at the 10% significance level, so on and so forth, okay? So kind of a nice example of type 1, type 2 errors. Let's say we assume the null hypothesis here. And this is a reminder. Probably should have put this in here anyways. I want to be able to type something in here. Insert. Where is it? Here. So let's say the null hypothesis is that someone's not pregnant, right? So just as a reminder that we have this up here, so you don't just have to hear me say it. All right.
I want to change that to a hypothesis, not an hypothesis.
Oh, that would help, right? There you go. So if we assume that the person's not pregnant, we then come back and the doctor says, no, we're actually going to reject the null and say that you are pregnant, right? Well, clearly here, they rejected the null when they shouldn't have been, right? Type 2 error would be if they come back, they fail to reject the null and say, no, yeah, you're not pregnant, when very clearly they should have been rejecting the null, right? So this is kind of just a nice setup for type 1, type 2 errors, just a kind of easy kind of way to see this without numbers, I guess. Okay, so if we know that type 1 errors is really represented by alpha, right? The probability of making a type 1 error is alpha, right? 1 minus alpha, probability you don't make a type 1 error. Kind of already went over this with the significance and confidence levels, okay? So we are going to be choosing the number of, or the amount of type 1 errors that we're willing to make. We'll choose alpha, okay? And it's always going to typically be these low values, and hopefully we can kind of see why. If I choose alphas of 0.01, 0.1, and 0.05, and I just said those out of order, but those corresponded to confidence levels of 90, 95, and 99%. Right? So we'll skip over type 2 errors for today, and I'll kind of come back to these next week. And then here's, hey girl, I made a type 1 error. I shouldn't have rejected you. I don't know. Sometimes I Google search for stats memes, and this one came up, and I thought it was funny. So how do we actually use this idea of a type 1 error? Look at the sample evidence we find, and then make a rejection decision, okay? So the first thing we look and say, is the sample evidence we found inconsistent with the null? If I'm assuming that the population mean is greater than or equal to 50, and I find a sample mean of 70, well, okay, great. I know I'm not going to reject the null because what I found supports the null. But if I do find something inconsistent, so if I assume that the population mean is greater than or equal to 50, and I find a sample mean of 40, well, now, is it sufficient enough evidence that goes against that null to which I can reject the null, right? So we have two approaches we can use, which is the p-value and critical value approach. Today, we'll just talk about the p-value approach, okay? Next class, I think we'll get to the critical value approach and make the kind of comparison of the two. So if we go back to this beer example, right? We had this null and alternative hypothesis, and here I'm writing the alternative hypothesis a little bit different. Because if you sometimes, I think some places in the text, but also if you I don't know, Google search help for stats homework or something, you will often see the alternative hypothesis written as H subscript 1, right? Also, I make that as a joke. You shouldn't be Googling it. You should just send me an email and I can help you, right? But what type of tailed test would we have here? We have a less than sign in the alternative hypothesis. So it's a less than or a left tailed test. So if I took samples of size 36, what would this distribution look like? Well, we kind of already, I think I drew it out earlier. We'll use whatever that cutoff value of 7% is, right, as the assumed true mean. Right? So I know that this distribution will be centered around that 7%, or I'm assuming that it's centered around that value, right? And I've got an assumed true mean. Now, if I see something like 4.5 as my sample mean, I know that if 7 was in fact the true population mean, it would not be very likely I see that. Right? If I saw 6.7, well, I know that's actually pretty likely. It's inconsistent with my null hypothesis, right? My null is that it's greater than or equal to 7. So it would be inconsistent, but not very unlikely for me to see that as a sample mean if, in fact, the true mean was 7%. Now, if I see 8.5 or 9.5, they're rather far from that 7%, but I don't have to worry about these values because these values actually support the null hypothesis. So I don't have to do any steps there. I know for sure I'm not going to reject the null hypothesis if I see sample means that support it, right? So we don't really have to worry about these, right? We know we're going to fail to reject, right? But, how can we say, if I just took 4.5, is it evidence that's unlikely enough if, in fact, the true mean was 7%? Is seeing a sample mean of 4.5 unlikely enough to where I can reject that assumed true value of 7%? Well, oops. Before we get to the steps, let's think about how we can approach this. If I assume that the true value there is greater than or equal to 7%, so I use that 7% as kind of my assumed true mean, what do I know is going to be true about the distribution of my sample means? I know it would be centered around that 7% because that was my assumed true population mean. I also know that if I see 4.5 and I want to figure out how unlikely was it that I saw something that far away from this assumed true value or anything even further away. Well, one piece of information that's helpful, and I think I give this to you on the next slide, but I want to do things out of order a little bit here. How would I find the standard deviation of my sample means? Well, I would have to know what my population variance was, and then I would divide it by my sample size. I know my sample size here is 36. Now, just like confidence intervals, we're going to start out with examples where we're given the population variance. In practice, it's more likely that we only have a sample variance, which we'll eventually talk about. But for now, we're starting out with scenarios where we assume that somehow we know the population variance, maybe like on a production process, but all we have to measure the mean is a sample. Well, if I have the standard deviation, I have a value for the mean, I have a cutoff value I'm interested in. Remember, how do I find the z-score for a sample mean? I take the sample mean, I usually subtract the population mean, but here I've got an assumed true population mean. And then down here, I'd be dividing by the standard deviation of my sample means, which I know is equal to that guy up there. So I have this equation. What we're going to call this, when I'm turning a cutoff value for the sample mean into a z-value, if I'm doing it by using an assumed true population mean, instead of like a z-value, we'll just refer to this as a z-statistic or a test statistic, okay? But it's really what we were doing before. It's just now we're using that assumed true mean instead of what the true population mean actually is. Once I turn this into a z-value, and I have this in the slides here in just a second, so if you didn't jot it down or something, don't worry, I'll put that formula back up here in a second, but I want to kind of complete this point. Once I know that I can turn 4.5, that sample mean, into a z-value, whatever that z-value ends up being, I can look that up in the table and find the probability that I saw a sample mean this far away from this assumed true mean. Right? So it's a little bit different now. Before, the z-value interpretation was the number of standard deviations away from the population mean. Now, the z-value, when we're calculating a test statistic or a z-statistic, is just the number of standard deviations away from the assumed true mean. It's really kind of the same idea, just technically we have to be a little bit different in how we say it. So if this probability gets really, really low, we're going to probably say, okay, yeah, we can reject that that's the true mean. Right? If this probability that I saw 4.5 starts to get low enough, then it's probably not likely that this, in fact, is the true mean. What I assume to be true probably isn't true, right? But how low of a probability is low enough, right? Well, if we go here, just to kind of recap, we'll calculate this test statistic, right? Once we have this test statistic, now we kind of can complete the example. So if I want to know how low is low enough, first I need to know, once I find that probability, I'll skip ahead here a little bit. Once I have that probability, we'll call that the p-value. If the p-value is less than the alpha that was specified, we can reject the null. So that's where we're going. We'll talk about how we find the p-values for a couple different types of tests. Why is this not working? Hold on. There we go. So just a reminder, here's our test statistic equation. We'll think about how we find those p-values, okay? So I've got some slides that have kind of the more formal, but I'll show you here. So this would be an example if I'm dealing with a left-tailed test, right? Once I convert that sample mean into a test statistic, well, now it's just a z-value that comes from the standard normal distribution. So I can look up that z-value, find the area to the left of it on the table. That's just my p-value. My p-value represents the probability that I saw the sample mean that I did if, in fact, this was the true population mean. That's the interpretation of the p-value. The interpretation of the p-value is the probability I saw the sample mean that I did if the assumed true value was, in fact, true. Okay? Or we could say it a little bit differently. It's the probability that I saw something however many standard deviations away my test statistic, whatever the value of my test statistic is, probably I saw something that many standard deviations away from that assumed true mean, if in fact it was the true mean. Okay? So once I have that p-value, if it's less than alpha, I can reject what I assume to be true. So for a left-tailed test, it's pretty easy. For a right-tailed test, it's a little bit different, right? So if I have a right-tailed test, we have some assumed true mean. For a right-tailed test, only evidence on the right-hand side would go against the null. So let's say I see something here. Now I want the probability that I'm that far away from the assumed true population mean or even further away. Well, I can turn this into a test statistic or a z statistic. But now when I go to the table and I look up this value, what's the table tell me?
What's to the left?
Yeah, the table tells me the area to the left, so I would have to just subtract it from 1. That's the only additional wrinkle with a right-tailed test, okay? And just as a hint, for most problems, the p-values should not be like really high. So if you make the mistake and forget to subtract it from 1 for a right-tailed test, you're going to end up with p-values of like 0.8 and 0.9. You're going to be like, something's weird here, right? Oh, that's a right-tailed test. I have to subtract it from 1. Now, two-tailed tests are a little bit different. And I'll put some actual numbers to this one. And I'll go back and I'll use that example where the mean retirement age is 67. So let's assume that I see 70, right, as my sample mean. I then say, okay, what's the probability that I saw something this far away from the assumed true mean or anything further away? Right, that represents my p-value. But the problem with a two-tailed test is I only got to see one sample. But I know if I saw something that was 3 above the assumed true mean, it was equally as likely that I had seen something that was 3 below that assumed true mean. And that also goes against my null hypothesis now. Before, with like a left-tailed test, yeah, it would have been equally as likely for me to see something that far away but below the mean. But the problem there was if I saw it on the other side of that assumed true mean, it actually supported the null. Now, if I see something on either side it goes against the null, right? So I only see one of these values, but I know that it would have been equally as likely for me to see, and I wrote 67 here. Sorry, what am I doing? Something equally as likely below that assumed true mean. So I'm really going to have kind of two tails here. Two-tailed test. You have a question?
Do you add them?
Yes. So, you know, depending on which one I see, here I said I saw 70. It would look very similar to what we did with the right-tailed test. I turn it into a test statistic. I can find the area to the right. But now this isn't just my p-value. It's actually only half my p-value, right? Because I have the exact same area over here. So if I find this area, I know it only represents half my p-value. To get my total p-value, I just add it to itself or multiply it by 2. Yep. Any other questions on that one? Okay. So I think in the slides, I have it written out a little bit more formally, I guess, here. Kind of for a right-tailed test, you're trying to find the probability that you saw something that was greater than your z statistic. Left-tailed test, probably you saw something less than your z or test statistic. Two-tailed test kind of depends. If my test statistic was positive, right? If I had seen this from my sample and my test statistic was positive, I had to find this area, then multiply by 2. If I had instead seen 64, then I would have to find the area to the left of it and multiply it by 2, right? It kind of depends there what sign my test statistic is. So we have kind of our different approaches. Here's, I think, a nice summary of the visual. I kind of did this on the board already, but right, left-tailed test, our p-values down here. Right-tailed test, this green area represents our p-value. Two-tailed test, the total in both tails, or that total green area would represent my p-value. Okay?
So what's up with the capital Z and the lowercase z? Is that anything?
Yeah, so you can think about it as, what's the probability I saw a z value? The capital Z is just like,
The number we use to find the score?
So think about it this way. When I'm drawing out these distributions with a standard normal distribution, think about capital Z. I'm really here. Capital Z is going to be what's on my x-axis here.
Okay.
Lowercase z is the test statistic, or you can think about lowercase z is your z statistic.
Okay.
So what's the probability I saw the z statistic I did for my z value or anything greater? And it's hard to distinguish between a capital and lowercase z when you don't kind of have, when you're not drawing things to scale real great here. Okay, so this is kind of how we find our p-values, right? Once we find the p-value, if the p-value is less than alpha, we can reject at that level, okay? So what are our steps, going to be? So we'll determine the null and alternative hypothesis. We'll then figure out what alpha level do we want to use. We'll calculate our test statistic. Using that test statistic, we'll find our p-value, and then finally compare that p-value to alpha to make our rejection decision, okay? So let's go through this example. Let's assume that the population variance I have known is 1%. Like if someone gives that to me, right? I know that the production process, that's the population variance. I still have the same kind of setup. Every other number's been the same. Can I reject this at the 5% level? So my alpha, 5% significance level, alpha of 0.05. Right? So if we go back to this example, first we figure out what the null alternative is. We've already talked about this quite a bit. The alternative was that it was less than 7, so we have a left-tailed test. Right? Our alpha level is 0.05. And from here, it's really just, once we had identified that test statistic equation, it's really just a matter of plugging our values in here. Our sample mean was 4.5. The assumed true mean comes from that null hypothesis, which is 7. Plug in our population variance, plug in our sample size, we get a test statistic of -15. Okay. So what would the area to the left of -15 be? yeah, if we're not completely used to these yet, these close on me. We may not be perfectly familiar with these distributions yet, but notice the lowest value on my z table is negative 3.99, and the area to the left of that is 0, pretty much. So the area to the left of negative 15 is just going to be really, really close to 0. Well, if I have a value that's really close to 0, right, my p-value is definitely going to be less than 0.05. If it's almost 0, my p-value is pretty much 0, well, that's less than 0.05. I can reject at the 5% level. Right? In fact, here, even if I did it at the 1% level, alpha would be 0.01. Well, a p-value of 0 is still definitely less than 0.01, so I could reject at the 1% significance level or the 99% confidence level as well. Okay. And then I like this meme to kind of go along with this example, right? Okay, so I want to go back and reiterate a few things. So when I started out with this null alternative hypothesis, right, what I was really doing, so kind of walk through the steps. I'm going to go through this visually with you. So we have my sample means, and I was using as the assumed true mean that 7%, right? Well, remember the null hypothesis that it was greater than or equal to 7%. So why didn't I choose 8.3, right? Well, if we think about this, if I build it around 7%, and I'm looking at 4.5, right? Remember, this area represents my p-value, okay? I could then, to find that p-value, turn 4.5 into a z-statistic to find out what that p-value was. And the z-statistic, it's a test statistic, but it's still coming from the standard normal distribution. It's still a z-value. So the interpretation is still the number of standard deviations that 4.5 was away from the assumed true mean of 7. Right? So it still has that kind of nice z-value interpretation. Now, if I, let's say that the variance was a little bit different so that I ended up finding that this p-value is something like 0.02, just for the sake of this, me walking through this. So at 0.02, it's still less than 0.05, so I could still be rejecting this null hypothesis. Well, I chose 7 because, let's say I did instead choose, remember, the null hypothesis was that the mean was greater than or equal to 7. So let's assume that I choose like 8 instead of 7, right? I just choose one of the other values in that range. If I use the assumed true value of 8, I know that my sample means would be normally distributed around that. Well, now if I saw that same sample mean of 4.5, what's the area to the left of that? It's going to be something much smaller, which means I would have a p-value that was less than 0.02. Well, if my p-value is getting smaller, I'm just even more likely to reject these higher values, right? Because if the p-value is getting small and I only reject when the p-value is less than alpha, well, if I can reject with the p-value for using the very lowest value in that range, then I could reject for every other value that was higher than that. So that's why we can use that cutoff. Okay? Any questions on that? So there's something else I want to give you a slightly different way of looking at that I think might help. Okay. All right. I want to reiterate something when we're talking about alpha. Right? So when I'm setting alpha, what I'm really saying is I have this assumed true value. And if I were to be able to kind of figure out what this cutoff was for the sample mean, alpha is really saying that, look, if I saw anything in this range as my sample mean, right? And let's for a second assume that what I was assuming to be true was in fact true. Let's assume that I had this as my assumed true mean. I don't know, a week from now, I can go back and figure out, yes, that was in fact the true population mean. But at the time, I saw a sample that was somewhere in this range, right? I know that if this was the true value, there would still be an alpha, like probability of alpha of me seeing one of these as my sample mean, right? So if I had seen any one of these sample means, right, if the area to the left of this is alpha, when I see this as my sample mean, the area to the left of that is going to be something smaller. So my p-value for every sample mean in this range would have been smaller than alpha. So I would have been rejecting for every single one of those sample mean values when in fact I shouldn't have been, right? So the idea of alpha is like, well, look, if I do see, I'll get rid of some of this to kind of make this point. If I do see something in this range, right, I know that the p-value, so you can think about here, this represents, well, I'm going to use colors here. Right, so here is my alpha. Let's assume that I saw a sample mean right here, right? So this red area represents my p-value, okay? So I know that for any sample mean that I see in this range, this p-value is going to be less than alpha and I'd be rejecting, right? However, if this in fact ends up being the true population mean, I shouldn't have been rejecting for any of those. So that's why alpha is kind of our type 1 error. We were rejecting when we shouldn't have been. So it's like, even if what we assume to be true ends up actually being the true value, we'd be making errors, say 5% of the time, if we set alpha to 0.05. But if we're finding p-values less than 0.05, like let's say 0.02, what we're really saying is, look, yeah, I could be making an error, right? I could be making one of these type 1 errors, but the probability that I saw what I did or anything further away from this assumed true value is so low, I'm okay. I'm okay rejecting it because I know that it's a relatively low probability that I am actually making one of these type 1 errors, right? So just another way of kind of thinking about this and starting to look at different areas in the graph and setting us up for some stuff that we'll probably talk about in next class. Okay. Any questions over any of this? Or so I think, just as a reminder where we left off here, we worked through this example. We'll pick up next class. We'll do another example with that kind of retirement age scenario. We'll then transition. We'll go through a couple other examples as well, but then we'll also look at sample proportions, right? So doing hypothesis testing for proportions when I only have a sample proportion. I don't think we'll get to do a lot of Excel work next class, but we might be able to do, we might do a little bit on Friday, right? Not related to your current Excel assignment, but for additional kind of future work. So unless there's any other questions for me, that Excel assignment is due at the end of the day Friday. If you have any questions, try to start working on that. Hopefully you've already put some work into it, but start asking me questions, today or tomorrow. If you end up trying to ask me Friday, I teach a large portion of the day, you're not gonna be able to get as quick a response on Friday. So get those questions to me pretty early, okay? Today and tomorrow. Anything else? Yeah, so I'll post an online quiz today. Should just be one question. It shouldn't be too bad. So get that done prior to the start of class on Friday. All right. No other questions? I'll see you guys Friday.